This is Jennifer Martinez, and in this video we're going to cover dimension and rank. So here's the definitions. The first definition on dimension. The dimension of a non-zero subspace H, and so this is what they denote it as, dim H, is the number of vectors in any basis for H. And they go on to say the dimension of a zero subspace 0 is defined to be 0. And then there's a little note at the bottom that says that the zero subspace has no basis because the zero vector by itself forms a linear dependence. In other words, suppose the basis for subspace H is the set B1, B2, all the way to Bn. Then the dimension of H is P. It's the number of vectors in any basis of H. And remember that a basis for a subspace H of Rn is a linearly independent set in H that spans H. And it can be shown that that smallest possible spanning set must be linearly independent. So it all makes sense. So what is the dimension of Rn? The dimension of Rn is n. Because every basis for Rn, it has n vectors. The standard basis for Rn is E1, E2, all the way to En. So it makes sense that the dimension of Rn is n. What about the definition of rank? The rank of a matrix A, has to do with the matrix A, denoted rank A, is the dimension of the column space of A. So rank A is the dimension of the column of A. That is the definition of rank A. So let's look at this example, example 3 in the book. Determine the rank of the matrix A given here. Well, here's the book solution. So what we're going to do is take and reduce A to echelon form. And doing that, we notice that the pivot columns, right, here's a pivot, here's a pivot, and here's a pivot. These are the pivot columns. So the basis is going to be the first, second, and third column of our matrix A. So it has 3 pivots. The rank is 3. So if you remember, the rank is just the dimensions of the column of A, and the dimension, the number of vectors in any basis. So that's why the rank was 3. Let's go ahead and look at another example. Let's find the dimension of null of B, where B is the following matrix. It's supposed to be a 1 right there. Okay. If you recall what the null of B is, the null of B is X such that our matrix, so we'll call it Bx, equals 0. So let's go ahead and find a basis first for B. So what I'm going to do is look at Bx equals 0, that matrix, and I'm going to row reduce this. So the first pivot is 1, and I'm going to get a 0 underneath it by multiplying the first row by 3 and adding it to the second row to get. Now I'm going to take -3, multiply the first row, and add to the third row. Finally, I'm going to get a 0 because now I have a new pivot, And I'm going to get a 0 under that pivot by multiplying the second row by 2 and adding it to the third row. And if you remember, the dimension of the null space has to do with the free variables. So here's a pivot and here's a pivot. So if we call this x1, x2, so forth, we see that x2 and x4 are free. So the dimension is going to be 2. If you want to see this, you could actually row reduce this and actually find the basis for the null space by solving for this solution, solving for x, and writing the answer in parametric vector form. But I'm just going to stop here and say the dimension of the null is 2. So, out of curiosity, what is the dimension of the column of B? Let's look at that example real quick, since we have the reduced echelon, or the echelon form at least. So here's my example. Find the dimension of the column of B, where B is the same matrix as our above example. Well, we see that this is the echelon form, and the basis has to do with the pivots. There are 2 pivots. So we know that the dimension of the column of A, which by the way is the rank, if you remember, is going to also be 2. Again, you can, the basis is going to be the first column and the third column of the original matrix. So there's 2 vectors in that basis, so therefore the rank is 2. There's an actual theorem that relates the rank and the dimension of the null. It turns out, let's see, there's 4 vectors here, and they're always going to add up to the number, the rank of A, and the dimension of the null of A is always going to add up to the number of vectors. Right? If matrix A has n columns, then the rank of A plus the dimension of A is n. So since this was 2 and there was 4 vectors here, 4 columns, then the rank of A must have been 2. Interesting. It does make sense though, because the rank of A, the dimension of the column of A, has to do with the pivots, and the dimension of the null of B has to do with the free variables. So it does make sense. So if we go back up to example 3, and I asked, what is the dimension of the null of A here? And you can go ahead and check this by looking at the null, finding the basis for the null of A. But here it is. There's the 2 free variables, x3 and x4, or sorry, x3 and x5. So there's 2 of them. The rank of A is 3, so the dimension of the null of A is 2. And that adds up to 5, and there is 5 columns in that matrix. So it does make sense. The next thing we're going to look at is we can now expand the invertible matrix theorem. It was long enough as it was, but now it's longer. So if you have let A be that n by n, and if you remember invertible matrix, because that was what is going to be equivalent to the first statement in the invertible matrix theorem, then the following statements are each equivalent to the statement that A is an invertible matrix. So A is an invertible matrix is equivalent to the columns of A form a basis for Rn. That actually does make sense because the column of A is precisely the set of all B such that the equation AX equals B is consistent. We'll look at that in a second. So therefore the column of A is all of Rn. That makes sense. The dimension of the column of A equals n, since the dimension is just how many vectors are in the basis, and there is n vectors in Rn. And P, the rank of A, is n. That's just this definition of rank of A is just the dimension of the column of A. The null of A is the vector 0. That makes sense because the null of A would therefore be there would be no free variables if the column of A is Rn. And therefore, the dimension of the null of A is 0. And by the rank theorem, the rank and the null do add up to n. So how are we going to prove this? The book proves this the following way. We just need to tie in two statements from the past, and then we will have all the middle statements. So they're going to apply G implies N, which implies O. I decided to copy the old invertible matrix theorem so we can see this. Here's the G implies N implies O, and then we're at P implies P, which implies R, then go to Q, and then we're going to go to D. And then we'll have everything. Oh, except for M. M is on its own. M is really equivalent to E and H. So let's look at that first. I kind of already said that before, but if you look at E, it says the columns of A form a linearly independent set. So all the columns are independent. H, the columns of A span Rn. So therefore, the columns of A form a basis of Rn. Because again, if you remember, the basis is the set that is linearly independent and spans our subspace, which in this case is Rn. So again, M is equivalent to E and H regarding linear independence and spanning. So let's start with G. I've kind of already said this in words, but let's do it in writing. Suppose exactly what G says, AX equals B has at least one solution for each B in Rn, where A is we're going to let A be an n by n matrix. So therefore, the span of the columns of A, A1, A2, all the way to AN, is Rn, where A is those columns, these vectors. By definition, that is the column of A. So we get the first one, we get N. And the rest just follow. So let's make this a little smaller. I know that's really tiny. Maybe I'll make that a little bigger. So we just proved N. So now we can look at O, which we know that there's N pivots in A, since the column of A is all of Rn. So therefore, the dimension of the column of A is N, which is, by definition, the rank of A. So you have P, which follows R, that by the rank theorem, that the null of A is 0, which follows Q, and then back to D.